Bene, buongiorno a tutti. I am pleased to welcome Professor Negishi, Nobel laureate in chemistry in 2010, here to the University of Pavia. Welcome to the University of Pavia. As you had, we had the opportunity just a few minutes ago to say something about the history of our university, and we had the opportunity to appreciate some messages coming from Alessandro Volta, who did not get the Nobel Prize because he was he was here a little before the introduction of the Nobel Prize. But also we had the opportunity to see something concerning the Nobel laureate in medicine, Camillo Golgi, 1906, as I told you. And we had here for 3 years Natta, whom you know very well, Nobel laureate in 1963, and also Carlo Rubbia, who spent here the last 7 years of his academic career. So we talked about history, and I would also add that certainly Pavia is constantly ranked among the leading research institutions in Italy. Pavia, University of Pavia is involved in many multidisciplinary research projects, both in humanities and sciences. And I talked to you before about Ugo Foscolo, who gave the name to this room. And I told you about his speech, his lecture in January 1809. Anyway, both humanities and sciences, let me quote here, but I could add many other disciplines, the fields of chemistry, of course, physics, nanoscience and nanomedicine, which developed quite a lot in the last years, and renewable energies. We have also a strong tradition of international student and teacher exchanges with many universities in Europe, Middle East, Mediterranean area, in the United States of America, in China, Japan, and many other countries. Our campus is unique, not only because of its prestigious historical origins and the top quality of achievements, but also due to its leading role in the so-called Pavia system, which includes 16 colleges and residencies. You just saw Collegio Borromeo. You will have the opportunity maybe to have a look also at Collegio Ghislieri. And there are 14 other colleges. And this is something unique in our country, something which is, let's say, approaches Pavia to the model of Oxford, Cambridge, and so on. And so, say, Professor Negishi, your visit and lecture is for all of us, and for our students in particular, a unique opportunity to listen to and interact with one of the most important scientists in the world. We know you were born in China, as we said before. You spent there the first 8 years of your life, then you moved to Korea, and then you are a Japanese, then you moved to Japan, and you graduated the University of Tokyo in 1958, and then you, a couple of years later, you moved to the United States. You started at the University of Pennsylvania, but actually you spent most of your time at the Purdue University. You got the Nobel Prize in Chemistry in 2010. Here there is a very long list of prestigious awards and honors, and I'm not going to read all of it, but I'm sure that it is really impressive. And in any case, since you are here, it is a very an important, real pleasure for us to have you here. A sign of our history is the Volta medal, la medaglia di Volta. This is an honor for you, since we are honored to have you here. So if you come.
I would like to talk about the magical power of transition metals, especially D-block transition metals. And I need to show you because in this glorious room, there's no periodic table. So I'm going to have to show you. And then today, what I would like to do is to briefly touch on the left-hand side of the scheme. This shows how our cross-coupling, Negishi, Suzuki, Tamao, etc., cross-coupling works. And the key player here is a transition metal. So I want to instill in your head, of course, we all learned from great chemists like Volta and Natta. So many of these pioneers. And in fact, I'd like to dedicate my lecture today here to Professor Natta. He was here, that's right. Yeah. He was here for 3 years. And indeed, my story on the right-hand side with zirconium, another D-block transition metal, which works as a catalyst, stems from Ziegler and Natta's work. We all must learn. We all learn from our pioneers, and then we just keep elevating the level of understanding. Okay, so let's start now. Okay, I don't need to dwell on this thing, but when we do chemistry, chemistry is in general hated by the general public. Very, very useful maybe, very, very necessary maybe, but it's dirty, it's polluted, and so on. So we want to do chemistry in green way. And many people say, don't use metals, because use of metals means not green. I don't understand. So I am totally opposed to that notion. If by using metals, if we can achieve five things, which I show here, in high yield, you put in 100 material, then you want to come up with 100 material product that you want, if possible. High yield, and then efficiently. You don't want to go through many steps unless it is absolutely necessary. We want to make what we want in as few steps as possible. That's efficiency. Efficiency, E. And then, of course, we want to make necessary organic compounds. Many things are organic. We are predominantly organic. What we eat are predominantly organic. What we wear, predominantly organic. And even in construction, where in Italy, of course, I'm in trouble. Materials are mostly heavy, inorganic material. But still, look at this. Carpet, and a wooden floor. All these are organic material. So, but important thing is we must make them selectively. And in today's talk, I discuss how we can synthesize right-handed molecule and or left-handed molecule selectively. You know, they look alike. They look alike, and under many conditions, they are almost totally indistinguishable. But our bodies and many naturally occurring organics, they can distinguish readily right-handed and the left-handed molecules. And I always talk about the story of, disastrous story of the thalidomide. I forgot which hand, because you cannot tell which hand was a good one. One-handed thalidomide was an excellent tranquilizer. But the other hand of the thalidomide, if taken by pregnant ladies during a certain period of pregnancy, that will lead to deformed, childbirth. And that's enough. I mean, we have to synthesize these handed, chiral, optically active, all these are equivalent words, organic compounds selectively. How selectively? Well, at least 99% selective. Otherwise, you cannot even sell as a pure chemicals. But in this case, when your health and bodies are involved, I would say as selectively as needed. So if 99.99% level of purity is needed, we should be able to synthesize thalidomide or whatever chiral compounds, handed molecules, selectively at that level. If you say 99.99999 whatever percent selectivity is desirable, we now, over the past few years, we have reached that level, final, pinnacle level, for the first time in history, for the first time in the world. That's why we are very, very proud. And that's the story, essence of today's story. How to synthesize handed molecules, along the line of Giulio Natta and so on. Okay, so, and of course, why all these high yield and efficiency and selectivity are needed? Well, because they translate into economy, but perhaps more significantly, as I just told you, safety. So, Y-E-S-E-S, yes. That's what we started hearing from President Obama 4 or 5 years ago when he started campaigning. So I got this idea from him. So yes, yes. Okay, and in short, as Mendeleev in Russia told us, yes, we must consider all usable elements. There are only 110 of them. But in reality, about 40 of them, 30 of them, close to 30 of them are intrinsically radioactive, dangerous. We should, in general, stay away from them. And yet another, some others are inert gases, and we need it, but you don't use inert gas in an intimate way in most of the organic synthesis. And some others are intrinsically toxic, about 10 of them. Okay, let me just show you another. Yeah, okay, so here's the expanded version of the periodic table that I like to look at and think, and there are 110 or so of them shown. And so red ones, beginning with 84 polonium, which Madame Curie discovered, 84, number 84. Then you see most of the higher ones are red, radioactive. We cannot use it. 26 shown. Intrinsically toxic ones, you see, let me see, pointer. It's okay. So, red framed one. So you see, the first one shown is beryllium, and then right here, cadmium. Rishi, thank you. You're always helpful. Thank you. And then cadmium. In Japanese, all Japanese know. Cadmium replaces calcium. Then your bone system gets eroded. So it gives a tremendous pain, and in the end, you would rather die. That was terrible. So under no conditions, I would say we should not use cadmium. Mercury, all Japanese know. Minamata disease. You know, some company through this mercury. Any mercury compounds that can be converted to a very toxic methyl mercury or whatever. And then the fish started jumping, you know, they became crazy. Minamata disease. We should never use it. Barium is likewise. Lead. Tin is a suspect and toxic. And I would not use tin. And this arsenic and so on. So there are about 10 of them which we should avoid. And as I already told you about is inert gas. Okay, and organic compounds, usually most of them consist of 10 elements. Hydrogen, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 shown halogen. So these are organic compounds. But we don't need to just stick to these 10, 11 elements. We can bring in metals as reagents, catalysts, intermediates, in between, to facilitate the production of what we want, almost any of them. And what I am emphasizing today is here. See, that's why I chose this color, which is not yellow. Yes, it's yellow, but to me it's golden. Golden color, the 3 times 8, 24 minus 1 technetium, 23. 23 D block transition metals. The more we use wisely, cleverly, as a catalyst. Catalyst means if you put in one part of D block transition metals, then it will go around and around and around. How many times? 10 times? Yes, that's not enough. 100 times? Maybe. 1,000 times? 10,000? 100,000? These are good ranges, but for many purposes, we would like to ask them to turn around to make what we want, million times, 10 million, 100 million, billion, 10 to the ninth. Then I think we can talk about reduction of CO2, catalytic reduction of CO2, to produce a very cheap but useful materials. Okay, those are the goals for all of us, particularly for young people, hopefully, who are attending this lecture. But that's my dream, that's my story. And briefly, I'm trying to come up with this cross-coupling that I thought about, cross-coupling, when I was 26 in my second year at the University of Pennsylvania as a PhD student. And I was a darn good student first year in class and tests. But in the second year, I started experiments. I was a very poor experimentalist. So I should have blamed of course I blamed myself, but at the same time I blamed the state of the art of the organic synthesis back then. Why is organic synthesis so complicated, so inefficient, difficult? Shouldn't we simplify organic synthesis? That was my dream. And one thing which came to my mind was, can't we make organic compound? Most of them contains carbon to carbon single bond. Methanol doesn't have, but ethanol that many people like, there's a C-C bond. So the majority of them do have C-C single bond. Many have C-C double bond. Some have triple bond, but C-C single bond was the key. And to make those kinds of compounds, oops, next one, sorry. Okay, skip the next one. Yeah. Next one. These are Mendeleev's periodic table. And he listed them and discovered about 90 of them, 80% or more of all available periodic table he knew. Not only that, he laid them in a chemically very, very useful way. That's a periodic table. And you get to see this 3-4 story high periodic table in St. Petersburg, which I recommend very much. Next slide. Okay, next one, please. Yeah, okay. So I came up with a Lego game approach. So I thought, perhaps, if we prepare R1M, M represents a metal. R1 is a negative one. R1 negative, because metal is positive. And also we prepare R2X. X is electronegative, like a halogen. Then R2 is positive, X is negative. And if you mix them, then negative R1 and the positive R2, they should couple. So I thought. And of course, M plus M and the minus X, they coupled. That will give a tremendous so-called thermodynamic driving force, MX formation. So here is one excellent reason to use metal, to make everything thermodynamically favorable. That's one thing. Secondly, M can be M and X. R1 and R2 may be a very complex carbon frame, carbon structure. By placing M here, X here, you know the position of the coupling, selectivity, and so on. So it makes a ton of sense not only to use X, but use metal. There's a group of younger generation chemists all over the world, thousands of them. They think, well, Negishi, Suzuki, and Tamao, and others, they use metal. Chemistry is not green. So they try to avoid using metal, and then they struggle. And then their results are often far inferior. So I say, give us a break. Evaluate everything in the overall sense. So that's my message. But when I checked when I was 26, these are the kinds of organic groups for R1. These are kinds of organic groups for R2. And then about 100 boxes are shown here, not quite, but. And if you can make all 100 or so different kinds of organic compounds this way, that would be fantastic. And there was a reaction known where M is Mg or Mgx, Grignard, Victor Grignard. He won the Nobel Prize in 1912. That was the first Nobel Prize presented in the area of organometallic chemistry. But he didn't do any catalysis, no catalysis. And when I checked the literature, Grignard way, these don't work. These work sometimes, but many problems. So I was very disappointed. But then I thought, shouldn't we develop a better method for taking care of these things? Okay. This, for the same table, this is a picture. Actually, it's a little more greener because this one was several years old. So these things are becoming greener and greener. Some of these boxes are green. We just avoid these. I don't talk about this today. But so as you can see, most of the boxes are green now. So people say, "Wow, this is a revolution." Can you go back? Can you go back? Yeah. To go from here and then to this one. So this luckily was recognized by the Nobel Foundation. And actually, Professor Heck's chemistry is different, but Professor Suzuki, myself, received the Nobel Prize. Okay, next. Okay, so here there are such a group of brilliant people. So let me briefly challenge you. Okay. So why do we have to use metal? I already told you two reasons. One, MX bond is the most energetically strong. Okay, if I may go back briefly to that. Yeah, okay, this is fine. All right? In this equation, carbon-metal bond, carbon-halogen bond, carbon-carbon bond, and the metal-halogen bond. So these four species are involved in this reaction. Of the four, MX bond is the thermodynamically strongest because metal is the most electropositive and X is the most electronegative. Therefore, by using metal here and halogen or electronegative elements here, we can guarantee in essentially all cases, this reaction is thermodynamically downhill. But here, you all know there is one more important conditions for any reaction to fulfill. That is a kinetic barrier. Kinetic barrier. Okay, now let's talk about that next one. Okay, so we must lower the kinetic barrier. And can you go? Yeah, okay, maybe, yeah, this is it. So here, of course, Volta and Ampere and so on, so great chemists, scientists. So here, electron deficient, that's acid, right? Acid. You mix acid with the base, and then you know that they form a bond. Thermodynamically, usually it's very, very favorable, but there is a problem in this reaction. Have you ever thought about that? Thermodynamically, this reaction is okay, but if you consider this step, as base starts providing a pair of electrons to B to begin to form a bond like this, there's a problem. You should ask Volta, Ampere. They're gone. Okay, look at this. As B begins to donate a pair of electrons here, you reach this point, this kind of point. Then B, let's say both A and B are neutral in the beginning, doesn't matter. As B begins to donate, then it will be positively polarized naturally, right? Because it begins to donate electrons. Zero anyway. So it begins to polarize, positively polarize. As A neutral begins to accept a pair of electrons, electrons are negative, therefore A will be polarized, negative. what are the effects of this polarization? Positive and negative. Negative charge will naturally begin to repel electrons. Electrons are negative, negative and negative. B, as it begins to send pair of electrons, it gets positively polarized, then it begins to pull back the electron. Simple as that, but that is the origin of this kinetic barrier, much of it. That's the problem. How can we resolve, how can chemicals resolve this simple issue? It's a very simple issue. And this is the most important message that I can present to you today, on this one and the next page. So I hope you understand this chemical, the dilemma that the chemicals face. Next one, please. Solution came first from Fukui. His homo lumo orbital, so frontier, these are called the frontier orbital theory, which he published first in 1951, but I understand he was doing this with a paper and pencil during the World War II. Anyway, then next came MJS Dewar, who published this scheme, which I post all over, and then I worship, and then I think with this scheme by MJS Dewar, published in 1953. He's the only one who didn't win a Nobel Prize on the list of 4. Fukui won with Lord Hoffman in 1981 for this work, frontier orbital theory. And Woodward was Hoffman's teacher, professor. He already had won in 1965. I think Dewar should have won, but that's how the world rolls. Okay, but what is shown here is the reaction of D-block transition metal, typical D-block transition metal species. And then what is shown here is a frontier orbital, HOMO and LUMO of olefin, alkene, representative organic compound, okay? So dark part has 2 electrons, HOMO, here as well. And the white part, 4 together, represent the LUMO, empty orbital. And here, empty orbital, LUMO, of the metal, okay? So now you have to think not only just the HOMO, but the HOMO, and the LUMO, and the LUMO, okay? So Fukui said interaction between this HOMO and the LUMO of metal, and then the HOMO of the metal and the LUMO of the olefin, or whatever, organic compound. Those are the most important. They represent greater than 90% of all forces. Okay, so what does this mean? 2 pi electrons of the olefin, HOMO, they are to be fed to the LUMO of the metal, empty metal. Okay, that's one way. 2 electrons are to go up from, as shown, from olefin to metal. Okay, in this process alone, there is that polarization, ill effect of polarization, raising the kinetic barrier high, okay? But in this scheme, synergistic bonding scheme, there's the other 2 electrons of the transition metal. They are to be fed to the LUMO of olefin. 2 go up, leading to charge separation, polarization, but at the same time 2 go down. and leading to charge separation. But this charge separation is opposite in direction. Plus, so plus, minus, and plus, minus. You add them up, maybe nearly zero and nearly zero, thereby lowering the kinetic barrier substantially, like 25 to 30, 35, maybe 40, from this high transition, the kinetic barrier, down to 20 or 15 or sometimes 10. Then these kinds of processes go very fast and in a reversible way. You might say orgious way. This is a key discovery. Therefore, not only accepting Dewar, Fukui, Hoffman won their Nobel Prizes in 1981. Woodward, he passed away, but he earlier, before 1981, but he earlier, already in 65, he already won his own. So many people speculate that had he stayed alive, he would have won the second one. And I fully agree. Anyway, this is so important. Okay, but most important message that I want to give you today, which I sort of come up with on my own, but I'm not taking any pride in it. So it's just very necessary thing. If you keep looking at this thing, then suppose you replace butterfly-shaped dehybridized orbital containing 2 electrons with a sigma orbital, metal hydride. From the point of view of Woodward-Hoffman orbital symmetry preservation rule, there's nothing wrong. Fundamentally the same. Okay. So, with this empty orbital alone of the metal hydride, they should add olefin very fast. Very fast. No wonder hydroboration of Professor Brown with B. Very fast. Room temperature, 0 degrees, minus 25, minus 50, minus 78. Still very fast. It makes sense. Okay. Hydroalumination, of course. But hydroalumination, aluminum compounds are tightly dimerized, as you know, or oligomerized. So they have a little extra problem. But fundamentally, hydroalumination should also go. And you can see. And hydrozirconation came shortly after discovery of hydroboration, which we use extensively. So I hope you get the picture. And so what is important here is also important here. There's no fundamental difference. Okay, if we accept that, suppose we replace this hydrogen with a carbon group. From the point of view of Fukui-type frontier orbital consideration, which has been expanded by Woodward and Hoffman, there is nothing wrong. Of course, carbon is sterically more substituted, not like a hydrogen. So there might be degree issues, but there is no fundamental issue. So I saw. And in fact, we discovered in 1978 zirconium catalyzed carboalumination reaction, which is nothing but one-step Ziegler-Natta type carboalumination, but with acetylene. And let me just go on telling you that I have taken care of hydrogen and carbon here. We already saw in the periodic table, there are many, roughly 70 or so elements that we can we can use. So you know how many others you can put here. Can you put metal? Of course. So you can call this a metallo-metallation. But, indeed, so here you have to be a little careful about the thermodynamic requirement. But when the metal here is boron, and so, this one is also boron. Already back in 1964, Michael Appert came up with boron-boration, which we use extensively. Okay, so as you can see, you have to watch out for the thermodynamic requirement. But other than that, there can be many other metals that can be placed here, or heteroatoms. In the case of heteroatoms, you have to be careful because, as I told you already, metal-halogen bond are thermodynamically strong. You have to break that strong bond and replace. Okay, so here is, I think, here in this slide, one slide, contains maybe thousands of papers, many works to be done in the future. But let me go on. Next slide. I have to go on. Yeah. So just if you could go back one. Yeah. So here I was emphasizing the significance of this empty orbital in hydroboration and other reactions. And in many reactions, like a Ziegler-Natta polymerization reaction of olefins, what has become very important is a superacidic species. How can we make superacidic species? Well, just by mixing these two acidic species, aluminum compounds on the one hand, and titanium, they had impure titanium in their reaction system as an impurity. That was the discovery of that Ziegler olefin polymerization. That's how I understand. Or it can be, if you replace a titanium with zirconium, then you can have a hydrozirconation and a carbozirconation. So those are the reactions that we were enjoying. And the superacid, by mixing two acids, you can generate superacid. George Euler, one of my heroes, very, eloquently explained this. So two Lewis acid with empty orbital, they come together, they try to stabilize, yes? This is a reasonably stable situation. But in a dynamic situation, they can break one of the four bonds. Here it is. This represents a superacid. So here it's an acid just like this one. But here, this acid is right next to this dipole. Positive end here, negative end here. Positive end closer to the empty orbital than the negative end. This leads to a superacid, typically strengthening the acidity by the factor of 10 to the 10th, or 10 to the 15th, 10 to the 20th, or even more. So that's a very, very general, important principle that we should think of. Put a dipole in this way, plus here, minus here, near this acid. Okay, I don't talk more about this one. Next one. Okay, next one. And okay, so very briefly, I will show you what we have come up with over the past 35 years. And we are very, very excited about this chemistry. And well, going back to cross-coupling, we, in 1977, we learned that it's not nickel. Nickel, 95% pure, or in this case, trans-cis cross-coupling reaction, 90% pure. To me, 95% purity is not pure. Very bad. 90% I cannot tolerate. 98% and above, chemical companies put pure chemical. Minimum 98%. They sell. Anyway, so we were not satisfied with the nickel. Then we screened the nickel, palladium, platinum. That's Mendeleev's teaching, suggestion. We did that. Out came palladium. So we were the first to show it's got to be palladium. Palladium catalyst. Platinum too stable, and it's not very useful. Besides being somewhat more expensive than palladium, you know. So when we switched to palladium, everything went greater than 99%. This one is a little low, but I think you can do that better. So if you use palladium, then you can hook two molecules, this one and this one, or this one and this one. Very, very selectively and clean. And I want you to remember that. Next one. And then I will skip many slides in view of time. Please, next one. And here's a demonstration relatively recently with a key, as you can imagine, chelating ligand. Two phosphines are tied together in an appropriate way. Then you can have a stable catalyst, stable but active catalyst. And you can turn the reaction over and over and over. How many times do you want to turn these reactions? Well, how about million times? So we chose these representative cases, and we studied, and then you know the 10 to the 6 is a million. More over million. We were very impressed. If you use palladium, right kind of palladium as a catalyst, one piece of palladium will go around and around and around, million plus times. If the palladium catalyst costs $1 million more, $1 million per mole, okay, per production of 1 mole of the product, 1 mole of the desired compound, actual catalyst cost is $1 a mole. Anyone can have $1 more and can give it to your friend or kids. It's almost nothing. That's the idea. And then someone said, million turnover number is okay most of the time, but for production of some drugs and so on, it would be nice to know that we can turn over, 10 to the 7s, 8s, and 9s. At the 10 to the 9th, a billion turnover number level, even if the catalyst is a little bit toxic, it's no longer toxic, effective. That's what people say. Next slide. Next one, please. And next one. So we can synthesize almost at will these kinds of compounds as essentially pure species in a pretty efficient way, in a predictable way. Next slide. Next one. So I just want you to enjoy the structures of these and the high overall yield and overall efficiency, and above all, overall purity of the product. We are very, very proud of. Next slide. Next one. Next one. And you know that these are relatively recent work. Next one. Next, please. Next. Next. Okay, so here very briefly. If you octenoid, these are called 1, 2, 3, 4, 5, 6, 7, yeah, usually there is some, this trienoid. Double bond can be cis or trans. 2 times 2 times 2, there are 3 of them. So 8 isomers. All 8 isomers, only 2 years ago we published. We prepared them all as essentially perfectly pure, but we claimed only the 98% or higher purity. And as you can see, yields are uniformly high, purity uniformly high. And this one is different from this one, which is different from this one, and this one. 1, 2, 3, 4. But to fully prove that, we have to synthesize 8 possible stereoisomers. Next one, please. Okay, so 5th one, likewise. 6th one, likewise. Next slide. 7th one, and 8th one. All in a predictable way. Okay, so this one was, these two are actually somewhat, they gave us a little momentary difficulty, but no problem. High yield, high purity. This is a Z, cis. Okay, so next slide, please. What these results gave me an idea or hint. If we can prepare these intermediates, which are chiral, containing asymmetric center, pure, then we can synthesize handed compound, which are much more difficult to synthesize or thought to be very, very purely. And that proved to be true. Next slide. So CoQ10, someone, my friend is trying to industrialize this next one. Okay, now these compounds. How do we synthesize these compounds? There's no double bond, no unsaturation, and there's asymmetric carbon center all over. When you see these wedged line, that means methyl group is pointing towards you. And in some cases, you may see a broken line. Then that methyl group pendant is pointing away from you. Next slide. Okay, how to synthesize? Well, first thing is I thought of one-step Ziegler-Natta polymerization reaction. Ziegler-Natta polymerization. All of them are preoccupied with how many times they can link together, and of course in an asymmetric way, as asymmetric as possible. But what I wanted in this case is a one step. Just add once and then stop. And it was not so easy. Actually, it was not so easy. I don't give you all stories today, but here is an alkene and alkyl aluminum compound and a zirconosine compound which came from Gerhard Erker in a timely fashion. We screened about 15 of them. They all work. But Gerhard Erker's compound, this one here, bis-neomenthylindonyl zirconium dichloride, that's the name. That turned out to be the best among those screened. So with this as a catalyst, then R2, 3 of them are bonded to aluminum. R2 adds here, aluminum adds here. Stop. Because of this bulk and other conditions. So that's why I call this a one-step Ziegler-Natta polymerization reaction. And then oxygen oxidize, you get this. Oh, sorry, that's a warning sign. Give me 5 or so minutes. Okay, so next one. All right. So I need to skip these. And we had a great fun in exploring this whole area, and starting from terminal alkene. And this is Sigla, not a polymerization, but we use a zirconosine derivatives, and that's a Kaminsky version. But anyway, we just want to add once and stop. And this is the reaction which slowed us down by 15 long years. It took me 17 years. And for the first 15 years, we were bothered by this one without noticing. That was my silliness. Next slide. Next slide. Okay, once you achieve this, then we have aluminum compound. Okay, as you can see, if you iodinate, you get iodide. Protonate, you get hydrogen. Oxidize, you get alcohol. Carbonylate, you get aldehyde. Carboxylate. But what is very, very important is palladium catalyzed cross-coupling. And as I told you, palladium catalyzed cross-coupling will not disturb any part of this carbon group. So this asymmetric center is perfectly preserved. That's the key. Okay, next slide. So observing that, and I need to skip this one. I need to skip this one. Yes, this is an interesting part. Let's skip. Okay. So once you obtain the chiral aluminum compound, then you can feed that to our palladium catalyzed cross-coupling. We can preserve this everything around this asymmetric carbon center. So if you feed 99% pure chiral species aluminum compound, then you get a 99% pure organic compound. If you can jack it up to 99.9999%, then we get a 99.9999% pure organic compound. That is, we have demonstrated, probably by now more than 100 times. So you have to take my word. Okay, next slide. And the purity is really, really high. It can be high. Next one. And I have to go on further. Here it is. Go back. Go back one. Here's aryl alcohol, simple aryl alcohol, functionally rich. There's OH, there's a terminal double bond, but no stereochemistry. It's typically $1 per mole, free, by today's chemistry standard. Bacamole, and we call this methyl aluminum iodination reaction. Methyl alumination, asymmetric one. Zaka reaction. Why? Zirconium catalyzed. Catalyst is zirconium. Asymmetric. A. Catalytic addition reaction. Zaka reaction. You go from here to here, which is typically 91% S, 80-ish% EE. Not highly pure, but important point here is that there is one asymmetric center, and then there is this oxy functionality, which makes the purification of this species very easy. Not only that, there's yet another heteroatom, iodine. Iodine is a very cooperative element, heteroatom. Both very close nearby, the alpha position, next position. So what we have discovered is that this compound 1 can be purified as much as you want just by using the right kind of lipase catalyst. I'll show you the results. And okay, next slide, please. So, suppose you can purify this. You purify this one. And then hook, feed this into all kinds of Negishi, Suzuki, whatever, cross-coupling. Then you begin getting various kinds of organic compounds. And as I told you, guaranteed, you can do this without disturbing the asymmetric carbon center at all. Okay, at all. Next slide. I skipped this one. Yeah, please. Okay. And skip this one. These are the kinds of total synthesis that we have published relatively recently. But that's not the main subject. Let's skip this. Okay. Cute little synthesis of this compound, but I'm going to have to skip this one. So I also skip this. So selectivity factor that Professor Charlie Shih at Wisconsin, who published this paper in 1982. This is a kind of Bible for us. So selectivity factor, E factor, when the E factor is high, how high? Well, anyway, we can do a very easy purification. So you saw this compound. With iodine, the E factor is 33. That's very high. So that means this compound is very easy to purify by lipase catalyzed acetylation. Aromatic group, unsaturated one, 42, even higher. Or other unsaturated groups like alkene, teens, they're not very high, but they are still quite cooperative. Now, simple alkyls like this one, 5, 6, or even less, very difficult. Very difficult to purify. So if you make these compounds and try to purify, then you're a loser, a bunch of losers. Okay, so don't do that. Many groups have done that. We have also done that. Then how we learn? So the key is to avoid making this one and try to purify. That's a bad way. Well, you purify this one, for instance. Now, many of you notice that. Okay, if you can purify this when it's easy to purify, do that, and then cross-couple to make all these things. Then it should be easy. That's the idea. But it came only recently to us. Next slide. So, okay. Here I want to show you that, with the phenol and so iodine as well, but you can purify to 99% level using, well, we like to use Amano brand, PS, AK, or sometimes PPL. So you have to experiment with several commercially available ones. That's all you need. Next slide. Okay, so so here, one step you go here, and second step you use Amano PS, and then we modestly claim the 98%, but as I told you, in this way, we can make these two compounds as pure as you wish in a practical way. We have gone to 99.9999. That's about the limit that we have gone. Okay, next slide. So, as you can imagine, when these two groups at the chiral center are very, very similar, methyl and ethyl, or ethyl and propyl even worse, or C5 and C6, impossible to separate, as you can imagine. When these two are similar, it's difficult. But ultimate one, which I want to show you today, is that these two are isotopically differentiated. And as you can imagine, those would be even more difficult. So this one is a proton containing acyl group here. And this one is alpha beta trideuteryl acyl. Both acyl groups, but isotopically labeled. One is isotopically labeled. Those are the ultimately difficult ones. And to my knowledge, there has been no. Some have attempted, some have succeeded, but they went through circuitous, very difficult roundabout route. And I don't think that they reached a very high purity. But using the trick that I showed you, there's no problem. Next slide. That's all I wanted to show you, and that's the end of my talk. So, bacamol, allyl alcohol, you make this one, they are not pure. 80, 90% EE. So that they are typically 90 to 95% pure. Okay? That's what EE means. Oops. Okay, so what do? That's the time when you should purify, because this compound has OH. OH, as you can imagine, has a high, selectivity factor, high E factor. Iodine, as I showed you, 30 or 35, I forgot which. Also, very easy to say, purify. With both of these present near this asymmetric center, beta position, or alpha position, or beta, you can readily purify this thing to greater than 99% EE purity. Okay, in this case, you get this one. In this case, you get this one. Sorry. Then, cross-coupling. My, oh my, they never do anything bad in this respect. If you have a 99.99, we establish that you get a 99.99% pure. This one. You change this one almost at will to the variety of compound. Next slide. Okay, skip this. Skip this. Okay, now you notice that with amano, whatever, PS, KK, you can get to the level that you want. Next slide. And so now I just show you a few. So methyl, ethyl, very difficult. No problem. Methyl and CH2D, so only deuterium, one hydrogen is replaced with deuterium. Previously considered to be next to impossible. No problem, very easy, pure. Next slide. So let's just, I hope you can browse through and enjoy. Okay, so here, ethyl and the CH2CD3, I already showed you. Next slide. And we don't cheat. We experimentally prove, if this were racemic, one isomer will show this much, the other isomer will show these two big ones. Now R isomer, if the R isomer is pure, then these two only. There's nothing, just a dead flat. You can easily say that it is greater than 99%. Or this is by NMR, this is by chromatography. Also, this one, there's none of these. This tiny one is this. Next slide. These are even more examples. Next slide. So you can tell. And by the way, we're not just playing with the toys. That is the bell. Thank you. Even this one, my friends have had a very difficulties. 10 or more industrial groups are trying to synthesize this as very highly pure compound. Why? Because if you oxidize to carboxylic acid, that has been a very promising anti-Alzheimer drug candidate. Naturally, they want to synthesize this one, but there was no good method before us. Ours is far, far superior, simpler, more efficient, and more importantly, purity, high purity. Okay, both R and S arundic acid. Next slide. More, but we just came up with a trick where we can establish first in beta position, alpha beta, and then you just move it around by tricking. Now this can be gamma, delta, epsilon, far away from OH. That you can do. Next slide. So here it's alpha, beta, gamma, no problem. Next slide. Here it is alpha, beta, gamma, delta, delta chiral, no problem. Next one. So next one. Here we have gone this far. Alpha, beta, gamma, delta, epsilon, no problem, but the problem is method of analysis. We know they must be pure, and whenever we established like this one, so they are pure. But when you don't show the EE, we have not yet, or some of them have already been established. But at the moment of this slide preparation, we were so confident, but we cannot claim. Next slide. And then came next one. Oops. More recently, we have come up with NMR method. NMR method. That will let us establish the purity, even when the chirality is alpha, beta, gamma, delta, epsilon. We go as far as epsilon, and from there on, I don't know. Okay, over the years, in the area of cross-coupling, more than 100 people. Luigi, where are you? Is this you? Okay. So, but I still think of the first quintet. They discovered, they did lay the initial foundations. Next slide. And in the area of zirconium titanium, there was a wild, crazy, but very brilliant David Van Horn. Came up with a triple bonded version. 17 years later, the one from St. Petersburg, Denis Kondakov, fantastic postdoc, and many others. Next slide. And more recent members, next slide. They are beginning to be dominated by people from one country, all of them. Next slide. Likewise, next slide. A reunion last year, maybe. Oh, here it is. And some of you may know this guy, Jim Tour, who succeeded Richard Smalley as a Smalley Institute director at the Rice University. He's been doing very well. Well, thank you very much for your kind attention.